So for part C, we are to find uh, d squared y dx squared. So what on earth does that mean? D squared y dx squared. D squared y dx squared is basically the second derivative of the original function. Okay. So C, we have to find. Let's write it down here. Find d squared y dx squared. Okay. This is simply d dx, the derivative of the derivative dy dx. Okay, so if you multiply to get d squared y dx squared. So we're just basically looking for the derivative of the derivative, the second derivative of y. Okay, so let's go ahead and write down the differential equation, which represents the first derivative, the y dx is equal to y plus 1 over x squared. Let me scroll up and make sure I got that right. Okay, good. So we're going to just differentiate this, okay? I'm going to be using the prime notation here just for symbolic convenience, and then at the end I'll revert back to the other notation that I have. So what we're looking for is the prime of this y dx prime. Okay, so this entire expression prime. Now, how do you find the derivative of a rational expression? Well, you use the product rule, right? So I'm sorry, the quotient rule, since you have a quotient of two expressions. So if you have u over v prime, do you remember the quotient rule? U over v prime is going to be v u prime minus u v prime over v squared. Okay, so we have low d high minus high d low over low squared. In this expression right here, y plus 1 is our u, and x squared is our v. Okay, so let's apply the quotient rule to this expression. Now you have to remember that you're differentiating with respect to x, so whenever we are differentiating any variable that is not x, we have to append d of that variable dx. Think about it as implicit differentiation. We're differentiating this implicitly since this is not an explicit function. When you're differentiating x's, you do not need to append any dd component because the x dx is just 1. But if you're differentiating y, you have to use dy dx because you're applying the chain rule here. Okay, so let me show you what I'm talking about right after I set this up. So we're going to have v, which is x squared, v u prime is going to be y plus 1 prime as vu prime minus u y plus 1 v prime is x squared, the denominator prime, divided by v squared. So v is x squared, so if we erase x squared squared, it's simply going to be x to the 4th. Okay, so x to the 4th. Now let's go ahead and differentiate this. We're going to have x squared. Differentiating this implicitly, the derivative of y is just y times dy dx, which is y prime, plus the derivative of 1 is just 0, minus y plus 1. The derivative of x squared is 2x using the power rule. 2x, derivative of x is the x dx, so that drops off, and we just have it like that. Okay, so do not forget to add y prime when you're differentiating the y term, right? And then the denominator is simply still x to the 4th. So let's see, simplify that. We're going to distribute x squared to that term right there, which yields x squared y prime minus minus 2x times y plus 1, okay? So let's write this down, 2x times y plus 1. I don't want to distribute this because I might be able to do a factorization later on, so I don't want to set myself up to fail. So let's leave it like that for now and make our substitution and see what we can do with that factor, that quantity in parentheses. The denominator is still x to the 4th. Okay, now what is y prime? We're now going to substitute the value of y prime dy dx equals y plus 1 over x squared into this equation to finish off the expression for our second derivative, okay? So let's plug that in. We're going to have x squared times y plus 1 over x squared. That's substituting y prime for y minus 2x times y plus 1. And that entire expression divided by x to the fourth. Okay, let's see if we can simplify that. If you look at this, inspect it closely, you notice that we can cancel these two terms out. And then we have y plus 1 minus 2x times y plus 1 over x to the fourth, okay? Now, you see what I was saying earlier about y plus 1 being able to be factored out? It can be factored out here, which makes our answer look pretty. So we factor out y plus 1, and we're left with quantity 1 minus 2x in the parentheses, and that divided by x to the fourth, okay? So that is the equation for expression for the second derivative. So the square y dx squared is y plus 1 times 1 minus 2x divided by x to the fourth. All right? Okay, now let's shift our attention to the next portion. Part D. We're to use our tangent line from C to approximate f of 1.1. And the question is this, it goes further to ask, is this a bigger or less than the actual value of f of 1.1, considering the result in C? All right, so what we're simply going to do is we're going to have this equation of our tangent line act like the function, and then we're going to use it to approximate the value of the function at 1.1, okay? All right, so let's go ahead and do it. So I'm going to call the tangent line L of x, okay? So this is part D. Part D, we know that the tangent line equation was y equals 3x minus 1. Let's call it L of x, okay? The linearization of the function, let's call it L of x, 3x minus 1. So f of x can be approximated using the linearization of the function. This tangent line, when you're really close to a particular point, L of x can act like a substitute for this function. Okay? So f of 1.1 is basically going to be L of 1.1, which is what you get when you plug in 1.1 into our function. So it's going to be 3 times 1.1 minus 1. Okay, so you're going to have 3.3 minus 1, which is 2.3. All right, so f of 1.1 is approximately 2.3. So the other part says that, is this an overestimate or an underestimate? Is it bigger or less than the actual value? So we also have to consult part C. So what does the concavity tell us about an approximation? So let's note the connection right here. So let's put a side note. Note the following. Okay. So note if the original function, if f of x is concave up, then the linearization of x is going to be an underestimate. Okay? Well, how do we know? Let's make a sketch. Let's say you have a concave or an upward function with upward concavity. When you draw a tangent line at any point, what do you notice? The tangent line is underneath the curve. Okay, so if the function is concave up, the linearization or the estimation with the tangent line is always an underestimate. All right? How about if the function is concave down? What do you think is going to happen? If f of x is concave down, then the linearization is an overestimate. It's an overestimate. Overestimate. Okay? So we have let's draw an example. Let's see. We have a function that's downward facing concavity on an interval. What do you know about the tangent lines on that interval? Wherever you draw the tangent lines, they're going to be it's going to be above the curve, right? So when you make any estimation, it's going to be higher than the actual curve. All right, so you have an overestimate situation here. Okay, so what rule does the second derivative tell you concerning concavity? And you also have to recall that if f double prime is greater than 0, if it's positive, then the function is concave up, right? And if f double prime is less than 0, then the function is concave down. So all we just need to find out now is the sign of the second derivative. What is f double prime at x equals 1? Okay, so we're looking at x equals 1 because that's relatively close. That's what we use to write down the equation of the tangent line. Remember, we found the equation of the tangent line at x equals 1, so that's what we're going to be looking at right now. Okay, so we're going to find dy dx at x equals 1. So f double prime of 1 is equal to what we found before, d squared y dx squared, evaluated at the point 1 comma 2. Okay, so let's make sure I have this right. Yes, I do. Okay, so what is d squared y dx squared? That's what we found over here. So we're just gonna plug in 1 and 2 into this function, and that should help us determine what our result is going to be. All right, so all I care about actually is the sign. Okay, so y plus 1 is 2 plus 1 times 1 minus 2 times 1 divided by 1 to the 4th. Okay, let's simplify this. This is going to yield 2 plus 1 is 3. 3 times 1 minus 2 is negative 1 over 1. I don't need to finish this off. I just need to determine the sign. Okay? So what does this tell us? Well, if we work it out, you can see it's negative 3. So f double prime of 1 is less than 0. So if f double prime of 1 is less than 0, that implies that f of x is what? Concave down. If f of x is concave down, then the linearization is going to be an overestimate. Okay? So let's go ahead and write that down. The approximation of f of 1.1, which is linearization of 1.1, is an overestimate. On the AP exam, you have to explain your reasoning. Okay, you can't just say it's an overestimate. It's an overestimate because second derivative of x is less than 0 at x equals 1. Okay, so since the second derivative is less than 0 at x equals 1, f of x is concave down, and the tangent line lies above the function. Okay, so that's the importance of the second derivative. It tells us the behavior, the orientation of the tangent line relative to the curve around a neighborhood, not at the point, because we know at the point the tangent line and the curve are indistinguishable. But if you go outside the point, this situation that we're writing down here holds. Okay. All right. So let's go on to the last portion.